Hi, I'm Dan Abel, and in this lesson, we're going to learn how to calculate the electric field when we get some distance away from a source charge. We learned earlier that the electric force is given by Coulombs Law, which is K, which is a constant, Q1, Q2, those are the two charges, divided by the distance between them. And the reason there's two charges is because any force is always an interaction between two objects. However, if we take this force equation and we apply it to a single charge, then we have the idea of the electric field. And the electric field is just the force per charge. So when we divide both of these by Q, that's going to eliminate or cancel out one of the two Q's in Coulomb's law. So the electric field, which is the force per charge, that's the left-hand side, is given by KQ over R squared. Let's apply that equation to the following problem. So we want to calculate the electric field strength at a given distance from a given charge. So for part A, we're 2 meters from a 1 Coulomb charge. And so if we take our equation, electric field is KQ over R squared. We're going to plug in K. Now, K is given as 8.99 times 10 to the ninth. However, in most cases, in most textbook problems, that can be rounded to 9. So 9 times 10 to the ninth. This makes the math a little bit faster. Then we have R as 2. And so a little quick math here, and we end up getting 2.25 times 10 to the ninth newtons per coulomb. We're going to use the exact same equation for part B. The only difference is now we're dealing with more realistic numbers. So, a coulomb of charge is pretty large. One electron and one proton is 1.6 times 10 to the minus 19 coulombs. And usually, if we're in the atomic world with protons and electrons, we're at a small scale. So 150 picometers is 150 times 10 to the minus 12 meters. And so when we plug our numbers into our equation, still the same K, we have Q, we have R, we need to make sure that we convert everything into standard base units. So instead of 150 picometers, I'm going to put in 150 times 10 to the minus 12 meters. Or you could have put in 1.5 times 10 to the minus 10. Run the math, and the answer you will get is 6.4 times 10 to the positive 10 newtons per coulomb. What's interesting is this field is actually stronger, even though the charge is much less. The distance is also much, much smaller, and it more than makes up for the reduced charge. And so just because I have a small charge doesn't necessarily mean that at the given location that the field is small. If I'm really close to that small charge, I'm going to have a really strong field. Big takeaway though is that this is just Coulomb's law applied to a single charge, and that's why we eliminated one of the two Q's.